Hey again, this is Professor Bennett from digitalaudiotheory.com, and this programming example comes from Chapter 5, which covers quantization. There's actually going to be two programming examples together, 5.2.1 and 5.4.1, to demonstrate the error that's introduced through the process of quantization, using a custom signal quantizer that we're going to make. Now, when an analog signal is sampled, its level must be converted to a digital value. And unlike analog signals, which have continuously varying level, a digital signal can only be represented with finite resolution, or the number of discrete representable levels. The resolution is governed by the bit depth, the number of bits of the ADC. With audio signals, we might typically see 16 bits, which gives us 65,536 quantization levels, or Q levels. 20 bits gives us around 1 million Q levels, while 24 bits gives us over 16 million Q levels. Some software packages and DAWs default to double type, which simply means two 16-bit words together to create a 32-bit value. That's over 4 billion Q levels for those keeping score. On the other hand, some music today is processed to recreate the sound of an 8-bit computer synthesizer with merely 256 Q levels. In this programming example, a very high bit depth signal, which will be treated as essentially continuous, will be quantized using a custom quantization function that we're going to call quantBits. You see that open right here, quantBits. In this function, a float value between -1 and 1, the input here could be a value or a vector, will first be multiplied by the number of quantization levels. Next, that scaled value will be rounded to the nearest integer, and finally divided by the number of quantization levels. This function effectively quantizes the signal to a bit depth of n bits, with an amplitude range that's also provided of a. Normally we're going to assume -1 to 1. Also, we can output little q our quantization step size. So we're going to save this. It's in the directory here for Chapter 5 from the Git repo. All this you can find on digitalaudiotheory.com. So we're going to use this function next to quantize a signal x. All right, here we are, programming example 5.4.1. We're going to create this signal x, and we're going to quantize it to 8 bits. We're going to call that x8. So x is going to have a magnitude of 0.5, frequency of f, which we haven't set yet. And then we're going to pass that x to our quantBits function. We're going to tell it to quantize to 8 bits. And we're going to pass, whoops, I'm in the, here we go. I was in the wrong, let me make sure I'm in the right function here. Signal quantization, here we go. Sample rate 1000 hertz, 4 seconds long. We're going to create our time vector going from 0 to 4 seconds. Our frequency is going to be 0.25 hertz. Our max amplitude is going to be 1. And we're going to specify a bit depth of 8 here. We're going to create x. Whoops, slide this over a tiny bit. Create x. Here's our magnitude 0.5, a frequency of 0.25 hertz. We've got our, I called it t, probably better call it n here. Let's call that n. There we go. Our samples divide by our sample rate. So let's generate these two. There we go. So by default, this signal x has a bit depth of 32 bits. So you remember that's 16 million Q levels, and we're quantizing it down to 8 bits, which is 256 Q levels. And a plot will allow us to compare the quantized signal to the original. Let's take a look here. Okay, let's blow this up a little bit so we can see what's going on. Let's zoom in. look at this. So the red one here is the X8, the 8-bit quantized version. And the blue one is our pseudo-continuous one, 32 bits, really, is what it is. And we can even check what our quantization step size is. Okay, let's try to get close to 0 here. All right, so we've got one value that should be right at 0. There it is. And our next value up is at 0.007812. Let's see how that compares to our quantization step size. So tilde means throw away that return. But I won't care about q. Remember, quant bit returns to q the step size. So let's see what that's calculated as. 0.0078. So our theoretical quantization step size matches our observed step size. All right, so let's go to the next programming example. This is 5.4.1. Okay, so you may be wondering what type of error is introduced by quantization. We can look at it. If we subtract the quantized signal from the original, then what remains is just the error due to the quantization. We're going to call that E sub q. That's what we call it in the textbook. So let's see. Here's our original and our quantized version. We actually don't need to rerun that. They already exist here in the workspace. But look, let's take the original and subtract the quantized version. We're going to save that in EQ. And let's plot it. Look at this. This is the quantization error. Note that in the plot here of the quantization error that the limits of the error are within the boundaries of plus or minus q over 2. Remember, our q is 0.0078. q over 2 is 0.0039. Look at this. The lowest error is negative 0.0039, while the highest error is plus 0.0039, within the bounds of plus or minus q over 2. It can also be seen that the quantization level is highly correlated to the signal x. Let's plot this. All right, look what I'm doing here. I'm going to take my signal x8, and I'm going to scale it down so that we can see it. And I'm going to change the ticks here. So on the horizontal axis, we go from minus q over 2 up to plus q over 2. All right. Now look what happens. When the signal is rapidly changing, as in this part of the cosine, the error rapidly changes as well, the quantization error. Versus if you look up here when the signal is slowly changing, or down here when the signal is slowly changing, the quantization error also slowly changes. Which is to say that the quantization error is tracking with the signal. It's highly correlated to the signal. And this correlation can result in a noticeable noise modulation that is sometimes audible, especially for very low level signals. In the next programming example, we'll look at the amount of error that is introduced through this process of quantizing. I hope you've enjoyed it. Thank you.